Yeah. All right. Hello, everyone. Good morning, good afternoon, good evening. Welcome to week 5 workshop of McMahon 2023. Today we have the pleasure to have Dr. Najeeb Khan to return as an instructor for our workshop. So I will go ahead and get started. As I mentioned yesterday, again, if you want to check the quizzes to make up any missing attendance, go on Gumroad, which I'm sure by this point you have signed up for. And filling the quizzes will make up any live sessions that you didn't attend for, and we'll take care of the total attendance and certificate issues in August when everything finishes. Thank you. So as mentioned many times, we have 2 phases this year. We're starting the second phase now, dealing more into the state-of-the-art, more advanced methods in medical AI, starting with today's first week 5 workshop in self-supervision and medical imaging. You can also go on our website to take a look at the schedule from today and going forward. Yesterday we had Dr. White Keys. Just to reiterate again, we have 2 amazing mentors this week, Evaxi and Ganta. They're in the audience right now as well for you to, and they'll monitor the chat, and if you have any questions, feel free to put them in the chat and they'll try their best to answer, as well as the Q&A session at the end with Najeeb. Yeah, so I will do a brief introduction of Dr. Najeeb Khan. He is going to talk to us about self-supervised learning. He is an adjunct professor with the Department of Electrical and Computer Engineering at the University of British Columbia in UBC. His research at UBC involves machine learning techniques for brain-computer interfaces, specifically for speech production. Prior to UBC, he completed a PhD at the University of Saskatchewan, Canada, working on regularization and interference acceleration techniques for deep neural networks. Thank you so much, Najeeb, for joining us today. The stage is yours. Go ahead. Thank you.
Thank you. Thank you for the kind introduction and for giving me this opportunity to talk about self-supervised learning. I'll share my screen. And now I will be looking at my screen so you would see me from the side, but I hope that's okay. Okay, so can you see my screen and my cursor?
Yeah.
Okay, cool. So we will share this notebook with everyone. So you don't need to type or sort of note anything. You have this Colab already with you. So what I will be presenting here is exactly the same as what you would be seeing in the Colab. It's just in a presentation format here. Okay, so just before we get started, I would like to put a few disclaimers that whatever I present here, all the images, I didn't create them. So if you want to use them or sort of wants to find out where they came from, you could just double click on any of the image, and I have the source provided there where the image came from. So that's now that it's out of the way, let's get started. So here is the outline of my of this workshop. So first we will sort of motivate why we need to sort of learn a new algorithm. We have learned a lot already. So what is the problem that's like we are going to solve? And is there anything else other than self-supervised learning that we could use instead of like learning another set of techniques? So that would be the first part, and I will take a break after this part and see if there are any questions or discussions that we can sort of address. And then the next part would be, what is self-supervised learning, or like how do we sort of like, how do you define it, or like what is involved in self-supervised learning? And then the third part is how do we do self-supervised learning? So we will get into the code and like actually implement a self-supervised learning method for image classification. So let's dive into the first part, like why do we need self-supervised learning? So let's start with supervised learning. So in supervised learning, you have seen it in the first 4 weeks. You have a bunch of unlabeled data. Well, in this case, you have data sets that were labeled by someone, by some learning team, labeling team. And then you have this nice labeled data set. And then you have some sort of neural network or any sort of model. And then you train using this data, labeled data, the model, and then the model can do predictions for you. So this is really good that we can do this, but this is problematic. And the problem with this is that you need this labeled data to start with, and you need a lot of it. For example, like to train like a simple image classifier, you might need 10,000, 50,000 images to do that. And this is expensive. So imagine you are solving a medical image classification problem, and somehow from sort of practice, you find out that you need 100K images. So if it is medical images, let's say these are chest x-rays, then you need really qualified people, radiologists, to label these 100K images. And if they take 10 minutes per image, then it's a lot of like time for 100K images. And in medical imaging, you don't just label one image per person or like one labeler per image. You need to have verifiers like, okay, is this really a malignant or a benign tumor or not? So typically you need 3 labelers per image. And so to label 100K images, you might need 24 person years. So if you want to do this in 1 year, you would need 24 people, something like that. And then time is one aspect, but it's expensive. So this, I gave an example of the medical imaging, but there are services out there that could do sort of labeling for you. And so I just searched a little bit, like how expensive is labeling? People say it's not that expensive these days. So I looked around, and AWS, which is a cloud provider, has a service that provides services for data labeling. So if you are doing, let's say, 1 million image labelings, so it would cost you around 20K. So it's not that bad. So I looked at Google. It's similar for 1 million images for image classification. It's 25K, which is just an example, ballpark number. But then they provide further sort of categorization. So if you have a segmentation task, it's like about $850K per million images. So even though it's not medical images, and even though the quality might not be like good, but still for 1 million images, it's a lot of money. So that begs the question: what are the alternatives to labeling lots of data? What can we do? So from previous weeks, you might sort of know that you can have better supervised training algorithms. So you can have data augmentation, or have better regularization, or change from neural network to decision trees, or from decision trees to neural networks. Do different sorts of things, and if a bunch of tricks in your sort of toolbox now that you could use. You could sort of think of like, what else would you do? I didn't list all the options, but there are a bunch of things that you could do with supervised training. So you should exhaust those whenever you have some labeled data. You might want to sort of try those out. And then last week or the week before, you looked at transfer learning. So that's if you run out of the other supervised learning tricks and tips and tricks, then you can use transfer learning. So if in the top image, you are training from scratch on chest X-ray data set. At the bottom, you have the ImageNet data set. You train the model on that, and then you use the weights from that model and train on the chest X-rays data set. So that works pretty good. But what if ImageNet and chest X-rays don't have much in common, which is mostly many times the case with medical imaging, is because they're very domain specific, and so even the X-ray images might not transfer well to, let's say, dermatology or other data sets. So what other alternatives are there? So another one is to generate synthetic data, and you would see these in the coming lectures as well. But the basic idea is, if you can't sort of label training data, then what you can do is just generate some synthetic data. And so people have generated synthetic data for medical imaging, and usually if you train with real and synthetic data, you get better accuracies or area under the curve in many sort of instances, in sort of skin disease classification and chest X-rays classification. So that's another alternative. And then yet another alternative is active learning. So if this is your passive learning, you have unlabeled data, you ask some people to label this for you, you have the labeled data, and then you have the AI which is trained on it, and you get the model. So that's the passive learning, or the traditional supervised learning. What happens in active learning is you have some baseline model, maybe like someone labeled a bunch of data and created this model, and then you ask this model to label some data. So you have these labelings for this data, but some of it might be very correct and confident, that the model might be very confident about it. And for some, the model would not be very confident about. And you want to filter out which ones are the ones that the model is not confident about. And then you ask the labeling team to label the data. And this is also a really good alternative to sort of completely sort of passive learning, where like the model has a little bit of a say in what should be labeled. So this is actively used in sort of almost all data annotation tools incorporate some form of active learning. So that's another alternative. But you could exhaust all those options. You could use them in combination with self-supervised learning. You could mix and match all of those. I just wanted to sort of lay the ground, like, okay, you might be thinking, what else is out there? So those were the things that we sort of already discussed. Now, what is why would we need self-supervised learning? And so here is a code. Like, a lot of the big names in AI are like betting on this self-supervised learning paradigm. And so Jan LeCun is sort of, he's the director of AI at Meta Research, and he's frequently quoted to say the future of AI is self-supervised. So why is that? So the reason for that is we have lots and lots of unlabeled data. So if you want to sort of find out medical images, you can find lots of them from different hospitals. Of course, there are like privacy and confidentiality and those issues, but that could be resolved, and then you could have some unlabeled data from different sources. But we don't have labels. So can we leverage unlabeled data to improve the performance of supervised learning? And the answer is yes, you can do that by learning good representations from unlabeled data. So here I just wrote some code to generate some circles. So here is scikit-learn is a library. It has a datasets module, and from that I imported the make circles, and I made 2 circles with some noise variance. That's 0.1, and one circle is half the other circle, and I just scatter plotted these points. So X is one dimension and Y is the other dimension, and here is the two circles. And if you want to classify these 2 circles, what you would need is, say you want to now classify the yellow from the blue, then you would need a bunch of supervised sort of labels. Like, you might want to say like, okay, given we are using supervised learning, we need to have like these data samples labeled. And if you have this this sort of data set, then if you apply some sort of supervised learning, let's say a neural network, it would learn a boundary between, like, it's something like this, and then in that case it would be able to sort of figure out like what everything inside the boundary is one class and outside the boundary is another class. So this is all good, but as you see, you need a lot of samples here in here. So I just am going to plot now something a little different. So here I was just plotting the data points. Now I'm going to plot the data points squared. So it's basically x squared and y squared. And it's just the same data with a different representation, right? I'll clean this up. Yeah, so now on the right side, you see that it's just the same data points, but squared. So here we see a really nice sort of separation. So even if you have two data points, like one maybe here, one here, and maybe one here, even a linear separation is possible. You could train a logistic regression to quickly just with just 3 samples separate these two classes. So that's the beauty of like good representations or representation learning. So hopefully by this example, we all agree that if we have better representation of the data, then we don't need as many data samples as are needed for supervised learning. So then why self-supervised? Like, representation matters, it's all good, but why self-supervised learning? So here is the sort of the step-by-step motivation for self-supervised learning. So supervised learning requires a lot of labeled data. Labeling is expensive. Large amounts of unlabeled data is available, and good representation could reduce the need for labeled data. So that brings us to sort of the core problem of self-supervised learning, which is basically to learn useful representations from unlabeled data. So that's why we need to use self-supervised learning, because we need good representations from unlabeled data. Okay, so so far we have discussed the why. Are there any questions thus far? Yijing, do you want to scroll through, and if there is anything that pops out?
Yeah, I think there's no questions for now. I think everything is very clear. Yeah, go ahead.
Cool. Okay, so now let's get started with the what. Like we discussed why supervised learning, but like, what is self-supervised learning? So it's a way to learn useful representations from unlabeled data, but you can't discuss what from like actually describing a little bit of how it works. So self-supervised learning has 2 stages, a pre-training and a fine-tuning. So here is graphic representation of the pre-training and fine-tuning. So in pre-training, we have a bunch of examples. So it could be, if it is an image classification task, we would have images and with no labels. And we train some sort of a model to learn the representation. And this part is basically trained using something called a pretext task. And we will look into this more next in the next few slides. But this is the pre-training part. And then once we have a pretext task trained representation, then what we do is we use this model, this representation, for fine tuning on our desired task. So if we are doing chest X-ray classification, then we would have inputs as chest X-rays and outputs as the labels, and we do the visual classification. Now, I have a quick question for you all. if that's the case, then we have you guys have already seen transfer learning last week. So the question is, what is the difference between self-supervised learning and transfer learning? So on the left side, we have what I described on the previous slide, and on the right side, we have the transfer learning. So take a moment and think about it. Like, isn't it just transfer learning? So the main difference is that in transfer learning, we have the ImageNet dataset or any dataset which has labels. So for example, in here, we have the ImageNet and we train it on the ImageNet dataset. We train this model on the ImageNet dataset. And we have the labels for each of the image in here. So if we have labeled data, then we can use transfer learning. But in the self-supervised learning, we don't have any labels on this data. And that's where the difference between self-supervised learning and transfer learning is lying. So as I mentioned, there are no labels in that there are the data that is used for training self-supervised learning algorithms have no labels. But how do we train the model then? We need labels. So self-supervised learning derives the labels from the input data itself. So here is an early sort of example from the 1990s. We will look into the modern ways of how we extract the data, the labels from the data itself. But here is an example. So in supervised learning, if you have an image of cow, you have cow is the label, and unsupervised, you have just the images and no labels. So unsupervised learning would cluster them or find some other patterns in it. In self-supervised learning, you sort of derive the label from co-occurring inputs. So if you see a cow and a moo sound, then you somehow associate that whenever you see a moo or hear a moo sound, it's most probably what you will sort of observe next is a cow. Or if you see a cow, most probably next what you will observe is a moo sound. So that's the general sort of initial beginnings of self-supervised learning in the 90s, but gives you an idea of like, and self-supervised learning is sort of a subset of the unsupervised learning. Okay, so this was a very sort of conceptual level understanding of like, okay, how does self-supervised learning works, but the methodical or sort of more formal way is the pretext tasks. The pretext tasks basically defines how to extract labels from the data. And there are three distinct ways in which we can extract these labels. And there could be more, but these are like the most common ones. One is context-based methods, contrastive learning methods, and generative methods. So we will go through examples of all these three methods. So the first one is context-based methods, and they basically exploit the spatial structure and the local and global consistency and data. So in words, it's a little sort of like not very obvious what do I mean. So let's look into some pictures. So here is an image, and it's unlabeled image here. And what I can do is I can make 4 rotation or 3 rotations of it. I can rotate it at 90 degree, 180 degree, and 270 degree. And then what I can do is I could just have a whatever model do I second, whatever model, whether it's a neural network, I could just input this image. And I know whether it's 0 rotation image or 90 degree image or 180 or 270, and I could do predictions of like what class does this image belong to. So 180 to 270. So it's like a classification problem with 4 classes. So now initially I didn't have any labels. I just had this image, I rotated it, created 4 classes, and I trained this neural network on this task. So this is a simple sort of way to derive labels for the pretext task. So that's one way. That to make it a little more sort of exciting and complex, if you have an image, you can make a few pages out of it. So if this is the whole image, what you could do is you could divide it into, let's say, 9 pages, and then take any page, for example, this one, and predict where does this this page belong. Is it to the top right or to the top left of this image? So you could have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these would be your class labels, and you input 2 pages, page 1 and page 2, and you predict whether it's in the top right position, like 0 or 1, or in the bottom right, the 9. So this way, if you don't know, if the model doesn't know, if this neural network doesn't know the internal structure of all the, like, how does a cake look like, it would never be able to sort of, or it would have a hard time to figure out where should this page lie. And so basically, by solving this task, the neural network would learn a representation that would be able to sort of figure out what am I looking at? Is it a cake or is it something else? So that's another sort of context-based pretext task that you could use. Yet another is the jigsaw puzzles task. And by the way, just to clarify, these are techniques that were used in like the 2015s, so kind of 8 years ago. So these were introduced back at that time. So the next context-based method is the jigsaw puzzle. So you have an image, and you take random pages out of this image, and then provide it to a network in random order, and then ask the network to predict the proper ordering of these pages. And so, even though for the original image you didn't have a label, but now for this image you have labeling. You know that, okay, this one should go at the first position at 1. The label for this one is 2. The label for this one is 3. So you have the labeling now for this image. So you somehow derived the labels from the unlabeled data. So that's the context-based methods. Now, so remember we had 3 types of pretext tasks that we could use. One was the context-based, the other one was contrastive learning, and the third one was generative methods. So the contrastive learning ones are more recent, or at least they are popular recently, like 2-3 years ago. And what they do is they make positive examples close to each other and negative examples far from each other in the latent space. So it's still a little abstract, so we will sort of dig a little deeper into it and define, like, how do we define positive and negative examples? We just have unlabeled data. So to do that, let's look at this example. So we have a cat and a chair. So, or we have a dog and a chair, sorry about that. And we sort of apply some data augmentation techniques. So for example, we cropped it here and here as well. We removed the coloring from here and enhanced or applied some color jitter onto this page. And then we pass it through some model, let's say a CNN. And once we pass both of these through the CNN, we know that this is the same image. Like these two are the same image. So we know the label for these two. Like this, for these two, the label should be that they are the same thing. So the output of this side of the network should be predicting that the difference between these two is very small. So they should be the latent representation of these two would be very similar. Whereas if we look at the chair and we pass it through data augmentation, similar to how we did what we did with the dog image. So in here we would again make these two augmentations to be very similar. The representation of these two augmentations to be very similar, but we want to make the dog and the chair very much different from each other. So basically, if we have the augmentations of the same image, then we want to minimize their distance in the latent space in the MLP output space. And if they are different images, then we want to increase their distance. So that's the basic idea of contrastive learning, and also this is the simplified version of it. So it was proposed in I think in a CVPR paper, and it's called Sinclair. I'm sure there would be questions about this, so I would be happy to answer them if there were any. So how do you what data augmentations could be applied? So for the dog image, we could keep the original, we could crop and resize, we could crop, resize, and flip. We could distort the color, we could apply some blurring, we could add some noise to it, we could cut some pages out of it, or we could rotate it. So these are sort of the data augmentation that were used by this paper. And then what is the cost function? So how do you define the similarity and the distance, and how do you train the model into it? So imagine you have so this here I'll describe a little bit about the whole process. So let's say you have a batch of images, and I would define it here is like this. So let's say we have 3 images. So image 1, image 2, and image 3. So no labels, just these images. So for each of these images, what I would do is I would derive 2 augmentations. So I would have image 1 prime and image 1 double prime, let's say. And similarly, for this image, I would have image 2 prime, image 2 double prime, and similarly for this one. So now I have before I had 3 images in my batch, and now I have 6 images. We could do multiple of these, but in 2-way Sinclair, this is what's done. So now think about it. Image 1 is image 1 prime is similar, like the same as image 1 double prime. So we should reduce that. So this is the positive example. It's called the positive. And image 1 is different from all these others. So all these others are negative examples for image 1. So given a batch of images, we do data augmentation to create 2 pairs, and then the pair, like if you have the augmentation of the same image, then that's your positive sample. And if you don't have and all the other examples in the batch are negative examples. And then what you want to do is you want to reduce the similarity between the same image augmentation to be small, to be large, and you want to increase the dissimilarity between I1, like and all other images in the page. So you want to increase this similarity between the positive examples, and you want to decrease the similarity between everything else. So this is how it is represented here. So we have the similarity between Zi, which is the latent representation of image I, and the positive representation, or the representation of the positive example of the image. So this is the similarity, and then we want to increase this, and we want to reduce the similarity with every other image in the page. So this is basically a softmax sort of cost function, but since it's doing the contrastive learning, so it's called noise contrastive estimation, or some sort of like NCE. So the official name for this is NCE loss. Okay, so we will see this in code, and we will come back to it, to this specific formula, but I just wanted to have a first crack at the formula. Remember that when I describe these image 1, image 2, image 3, these are the embeddings. So these are not the images themselves. These are the out. So this is the image. There are 2 augmentations, and then this part, Zi, is here. So we apply this cost function at the output, like in this latent representation space, not in the image itself. Okay, which is obvious from here. And then we do it for all the. So if we had n representations of the images, we would have 2n augmentations. So we sum it over the 2n. And then we want to average it over the whole data set. So that's where the averaging comes in. Okay, so these were, this was the simplest sort of contrastive learning algorithm that I described. Sinclair. Contrastive SSL is a really hot research topic, and a lot of things are happening in this area. If you are sort of looking for a method for medical imaging, it's good to sort of know that a lot of other methods also exist, and for the sake of time and sort of to keep the scope limited, I'm not going to describe all of them, but just listed the names here for you to sort of recognize that these are belonging to the contrastive SSL methods. Okay, so this was the contrastive methods, and we will see a coding example of the contrastive ones. But just for the sake of completeness, let's look at the generative methods, and these are really sort of the latest and greatest. And the main method in generative methods is the masked autoencoder. So the BERT models or ChatGPT-like models are also sort of similar in concept. Not quite, but very similar. So the same ideas are applied to images now, and so masked autoencoders are one continuation of it. And on an idea level, it's very simple. So you have an image, you make a bunch of pages out of it. So let's say how much are they? 5 by 5 pages, so 25 pages out of the image. Then you randomly break out certain parts of the image. So like 1, 2, 3, 4, 5, 6, 7, 8. So 8 out of the 25 are like kept, but the rest are like blacked out. And so the ones that you keep you pass it through an encoder, which is sort of a neural network, and it produces some output, and then you put the pages back into where there were like blanks. You put the blanks back in, which could be just zeros, and you pass it through a decoder layer, and the decoder tries to basically reconstruct the input. So it tries to have the original image. So basically, the input becomes like noisy input or like masked out input, and the target is basically the image itself. So the way to generate targets is basically we don't generate targets, we generate inputs, and the input is generated by just masking out the input, and that's basically how language modeling works. And so the idea in language processing is very old, but it's applied to images just recently because of the because in image processing or computer vision, CNNs or convolutional neural networks are very popular, and so this sort of masking doesn't blend well with convolutions. But now these encoders and decoders are sort of based on transformer models. And I'm not going to describe the transformer models, but basically what happens in the vision transformers is we basically page the image into a fixed number of pages. And so that allows us to like move away from the convolutions and apply this autoencoding technique to images as well. So pretty recent, and if you want to sort of look into the latest methods, then this would be a good one to look into. Okay, so are there any questions before we dive into some coding?
Yeah, I think we there's a few answers for this question, but a question about the loss function was asked about the tau term. I refer back to the original paper, and again to also refer to another paper. So the loss function of SimCLR, yeah, this one, CLR, yeah.
Yeah, so I skipped over the tau. It's I briefly described. So this is called the temperature coefficient, and so if you from softmax, so if you have so this is a very conceptual level sort of explanation, so it might not be if you know much more technical details about it, this might not be the most accurate. But let's say you have okay. So let's say you have a neural network and you have a bunch of outputs. So let's say you have 3 outputs. And so if you just use the like at the output of the neural network, you just use a softmax classifier, softmax of like whatever the pre-activations are. Then what would happen is most probably it would happen to see like, oh, a probability of 0.99 and then 0.005 and 0.005. So this would be sort of the output of the softmax. And this is okay, but this puts undue sort of probability or like undue confidence on the class that the neural network is predicting. So if we sort of and it has a bunch of reasons to sort of why this is bad, and one of it has to do with gradient propagation as well. So what happens is if we just scale the like inside the softmax softmax function, if we divide the pre-activations by some sort of annealing factor or temperature factor, so that then what happens is instead of like it providing like 0.999 for just one class, and it sort of humbles the loss or the neural network to like, don't be so confident. It could be like 0.1, 0.8, and 0.1. So it helps with like a bunch of issues. And this tau basically determines how much you are going to see the spread, and it helps with the gradient propagation and numerical stability and stuff like that, and optimization. So hopefully that gives you some idea of like where the tau comes from. It's called a temperature factor. Eugene, do you have anything to say on that, or?
Well, yeah, I think that's pretty clear. We have a few follow-up questions on the similarity functions, the cosine similarity. You can elaborate on this a little bit more as well, the sim.
Yeah. So the sim is a similarity function. It could be so basically what you do is you want to find the similarity between two vectors. So it could be any method. You could just take the scale dot product. So you have zi and zj, and then you divide it by zi magnitude and zj, so that large sort of vectors doesn't dominate the similarity or dissimilarity, and also to have a value between 0 and 1, or -1 and 1. And so that's the standard way to compute the similarity. And if you recognize this is basically the cosine between the two vectors. So that's one way to do it. You could also do Euclidean distance, but then that wouldn't. Then you would have to normalize that as well, because it wouldn't play very well with the exponentials. So yeah, it's just like for the purposes of this sort of algorithm, cosine similarity is used between the two vectors, but I'm sure there are other research works that just specifically investigate what is the impact of like the similarity function on the quality of the downstream classification task, or something.
Mm-hmm. And then we have another question regarding context-based approach, whether the idea is to learn spatial relationship between different patches. What's the, I guess what he meant was, yeah, this after.
Yeah. So I don't know if I understood the question, but I would just describe it once more. So if you have an image of a cat, so or like let's say you have a data set of like animals data set, right? And it's not labeled as okay, which animal is this? And there are a whole bunch of images, right? And now you want to sort of use self-supervised learning and use context-based method. So let's say you have an image of a cat. You just want the model to learn a representation that would be able to sort of recognize a cat in different scenarios. So sometimes you could only see the face of the cat in the image. Sometimes you could just see the ear of it. So if you can sort of figure out like, okay, which part of the image belongs where, so in that case, then you have sort of learned a good understanding of like, okay, what does the image contain, and then it would help you to do the classification task. So here we have we would have a full cat image, and then at some position, the neural network receives like, okay, at some position I have this image page 1, and tell me where does image page 2 fits in, right? And so then the task of neural network is to do a classification. This is not how it is trained, but I'm just simplifying for the understanding. The task of the neural network is then to classify, okay, given that image page is a head and image page 2 is sort of a ear, so it's a left ear, like right from the cat's perspective, but left from ours. So it's going to go to the top left. So top left is number 1 position. So it's a 1 in the output of the neural network. So out of the 9 classes, the label for this would be 1, like 1, and then the neural network would learn this using this supervised classification. So maybe does that answer the question, or?
Yeah, I think so. And then I guess before we move on to the coding part, you also showed a lot of other SSL algorithms other than the SimCLR. Let's say you have a problem at hand. Do you have some advice for our audience on which approach to choose out of what's available out there?
Yes. So if you're not doing research, like if you're doing research, then you better like survey the literature. I don't have any advice for that. Just pick the latest. But for practice, like if you have a real sort of data set that you want to sort of use, so then I think the latest pre-trained and sort of models are the ones that you want to use. So for example, these context-based methods. If you look at the contrastive learning methods, they already somehow incorporate data information, right? Like if your learning algorithm is predicting just the cropping or just the ordering, here it's doing much complex things. So I described the context-based methods just for the sake of completeness or sort of build their understanding, but you like the recent methods are like based on contrastive learning, and so definitely use something that's like recently being used. So I would definitely recommend contrastive learning, and then the masked image encoding, or like masked image masked autoencoders are the ones that are like useful for really large data sets. So if you have like really huge amounts of data, then the transformer models are like really good because they can consume like they can work really well with these sorts of data sets. So in here, like I don't know if like there's the Instagram 300 million image data set and so on. So those kind of scales of data are like really suitable for something like masked encoders. But the middle ground is definitely one of these contrastive SSL algorithms. I picked the Sinclair because it's easy and doable in a short sort of time, and there were tutorials available, so I just reused one of those.
And Jeremiah asked a question on what is the latest approach on SSL for tabular data? Great question.
For tabular data, I haven't. I'm afraid I might not be. As updated on tabular data compared to like vision or language. I don't even know if there is like good transfer learning methods for tabular data, because like if you have a bunch of like columns, how do you when you train it on one let's say Excel sheet, how do you transfer it to a different Excel sheet? But definitely a really good question. Like I would probably have to look into it.
I think I haven't seen much myself on tabular data, but maybe I'm missing out as well. I'll definitely take a look. And yeah, so I think it's a good time for you to go ahead.
Okay, so since my computer doesn't have a GPU, so I would now move to the notebook part. So just go all the way down to Okay, this is what I would be sort of walking you through is a simplified version of this tutorial. If you understand what I sort of described here, then you can go and take a look and look at the more detailed tutorial in the link. Okay, so I'll just skip on the imports and stuff like that. And let's get straight to the data set. So before like you start looking into medical images, or you want to look at some sort of typical data set for self-supervised learning, and STL10 is one such data set. I couldn't find what does STL stand for, but the STL website basically says it's a data set for self-taught learning algorithms. So I assume it's self-taught learning 10, but it could be something else. So this data set contains 500 training images and 800 test images per class. But it has a whole bunch of unlabeled images for self-supervised learning, for unsupervised learning, and we will look into some of the images, but there are like a whole bunch of unlabeled images, 100,000, and only 500 training images divided into 10 classes, which means or rather 500 images per class. So there are 10 classes, so only 5,000 total training images. So here, I would just briefly go through the dataset loading part. So whenever we are sort of looking at the PyTorch datasets, it's in the basic data is in raw format. So we want to perform some transformations on it. So the first one is we want to transform it into a tensor, and then we want to normalize its mean and standard deviation or variance. So this is the transform that we apply to the STL10 dataset. We load the training and the test splits out of there. So I'll run this. So this would load the datasets. It takes a while. And then here I'm just ignore the code, but just to see how does the dataset looks like. So it has images of animals and cars and ships. So if you have looked at the CFAR10 dataset, it has almost the same sort of categories. And so this is our dataset. It would take a bit to load, but let's move ahead. So remember the part where we said we will do in Sinclair, we would do the data augmentations, this part. So how do we, given a single image, how do we apply these transformations onto this data? So here I am defining like a transformations class, which basically is very similar to what we did here. We had this image transforms, and we sort of do a composition of different transforms. Here I just had transforming to a tensor and standardizing it. But here I'm going to do much more. So I'm going to do transforms dot random horizontal flip. So it would randomly, sometimes it would flip it horizontally. It would do random resize crop. So it would randomly crop it and then resize it back to the same size that we provided here. So 96 by 96 is our image size, data set size. So that's there. And then we will apply some color jitter, but we wouldn't apply it every time. So we would apply it with probability 0.8. Random grayscale. So if you look at here, you were like color distortion. So probably the grayscale just belongs to that category. So we can do, with some probability, we would do convert it into grayscale. We will do Gaussian blurring with a kernel size of 9. So it's like a 9 by 9 sort of page, which basically blurs the image. And then transform to tensor, and normalization is another way. And so given these transformations, I'm going to reload the unlabeled part of this data. This will take some time. And once this is done, this is applied to an image twice. So because we want to have like not just one, but two. So this is one augmentation and this is another augmentation. So for each image, I would have two augmented images. And the way it's done here is the transforms, these basic transforms that I define here are applied n views time, and n views is 2. So once this is run, let's plot some of the images. So this is that animal. I don't know what animal. So let's look at the car example. So here is the car. So it's not the full car because we applied some data augmentation on this, and now it's blurred and its color is sort of different. And also here the color should be different. It's not the original one because this is one augmentation and this is another augmentation. Similarly here, a truck, and so we have a sort of cropped and resized version of it. Here is the lizard or whatever animal it is, and then here is a different augmentation of the same image. So all of these are pairs, so 2 images each. So these basically gives us the augmented images for this training. So we have this part now, and we have this part now. Okay, so now I'm using or in here we would use the PyTorch Lightning, which is Eugene. Have we seen PyTorch Lightning, or should I briefly describe it?
Yeah, briefly describe it. Last year we actually had a whole workshop on PyTorch Lightning, but this year it was put as one of the online modules. So if someone has taken a look at last year's video, they'll know. But if not, probably
okay. I'll briefly describe it. So I'll just write a simple sort of So PyTorch Lightning is a sort of a simple way to run PyTorch training. So the way it works is you have like whatever class you like my model. So this is how you sort of define your model, and then whatever you pass in here is and it is stored in self.edge params, so you could access those from here. And then what does this my model is expected to have is a training step. And what the training step does is it does, like, given the batch of data, give me the loss function. So whatever is the loss of this batch of data. So batch of data is like x and y in it, so x and y, so inputs and expected outputs. And so here you would use whatever model you have, like whatever PyTorch model you have, you would call the model on, and it would give you an approximate answer. So given this page of data, you sort of unpack it, so it has the inputs and the outputs. You compute the approximate output using your model, and then you pass it to some loss function. So you have y a and y, and so this is all that it expects from you. So you would have to define the model and the loss function, and then you can just use the PyTorch Lightning .fit method. We will see more concretely. I'm just giving a brief high-level overview of how PyTorch Lightning works. So you define a trainer, and then after that you just run a fit method on the trainer, and then this just trains the models for you, and you can provide like the epochs as arguments and so on. But this is the basic structure of a PyTorch Lightning module, where you just provide the training step, it receives the batches, and you need to define your model and the loss function, and .fit method would run the training loop for you. So here, so we saw the images. Now we are going to define the actual thin clear model. So for this part, where was it? For this part, for the CNN part, I'm going to use a model in torch region, and it's the ResNet AT model. So if you haven't seen this, it's just a convolutional neural network with residual connections. It's quite popular. Please do review it if you haven't. So this is the part where we have this CNN. So this is the ConvNet. And then if you can see, there was like something on top of it, CNN. So here we have the CNN, and then we have this MLP. And we compute we take the output of the MLP as the ZI. So here I have the CNN, and then I take on top of that a few more layers. So I put in a linear layer on top of that. The actual numbers are not important as to like what is the dimensions and so on. You could just tweak these based on like experimental results, but the main components need to be understood. So self.convnet will now be our model in the Sinclair PyTorch Lightning module. And then this configure optimizer, this is just an optimization. If you don't provide this, it still will work. The performance would be really bad. But let's look at the training step. So the training step basically sort of receives a batch, and then it basically calls another function. So it just says, okay, I'm not doing any work. Let's let the info NC loss function do all the work. It just receives the batch, and it should return the loss function. So we need to look into more details of the NC loss function here. So here is the loss function. So we have the batch, and as we said, we wouldn't have any labels in this Sinclair. So we just have the images. We basically now we have two images, one after the other. So we need to concatenate these. So if I still have these, I think I erased it. But what basically we are doing here is if we have Z I or image I, then we had like ZI prime and ZI double prime, right? Two augmentations of the image. And so we want to like flatten this array. So we would have like Z1, 2, Z1, Z2, Zn. So these are the primes. And then we want like Z1 double prime, Z2 double prime, Zn double prime. So this is basically going to be after this concatenation. That's what our images would look like. So these are our images. And so now we would pass these through the CNN and the convolutional neural network to get the features. And now we have the features. And what we need to do is just compute the similarity between every single image with every other image. So it would be 2 bytes. So we have now this array, and now we need to sort of just find the similarity between, let's say, Z1 prime and Z2 prime. this matrix would now contain like similarities of all the pairs of features. And that's our cosine similarity. But of course, we don't want to have like similarity of we don't want these components like Z2 prime with Z2 prime, because this would be this would cause problems, because this would be 0 for us. So we want to delete like the diagonal items from this matrix, because that would be the minimum number then. So we would do that by just setting it to really negative number here, and then we basically for every time we go the page size. So for example, in here, I could do Control C. Okay, so I have to write again. So let's say we have 3 images, Z1, Z2, Z3, and Z1 prime, Z2 prime, Z3 prime, right? So the page size is 3. So I have the Z1 here, and its positive example is 8. Page size by 2. So they give 6 by 2 basically. 6 by 2. So 0 is 6 by 2. I would be I plus 6 by 2. So this is what's happening here with the masking. You want to find out which positions have the has the positive masks. So we basically shift the cosine similarity shape by the size of the matrix that we have divided by 2. So if our page size was 3, it would shift it by 3. If our page size was n, it would shift it by n. So this would give us the mask of the positive pairs. And now we need to calculate the loss function actually. So this term basically. So we have the exponential of the similarity of the positive example. So we already calculated the positive mask. So we would see the element. So we have cosine similarity. We divide it by the temperature parameter, the tau that we had there, and then we have the positive mask cosine similarity plus we use the log sum exponential trick to compute the log sum exponential here. So it's there, and this negative goes in, so this term becomes negative, this one becomes positive. So that's why you see a negative here, and then large log sum exponential of the cosine similarities. And this gives you the loss, but it's not it's not the mean loss, it's the sum of the losses. So you basically do the loss dot mean on it, and this gives you the mean loss. And so you just return, so this is the loss is computed, you just return the loss. The other things are just for logging purposes or setting up the like where to stop or things like that. So that's not important, but the main part is to sort of understand really well, like how does this code maps to what we had there. Okay, so that's the training step in the pipeline. Then is a sort of a way to train the models in PyTorch Lightning. You basically specify a PyTorch Lightning trainer, and it just takes in a bunch of parameters like, okay, where should it store the models? When should it store it? What should be the number of epochs? Which device should it store it? So there are a bunch of these parameters that defines the trainer. And then what we do is we get the the training data, the unlabeled data, and then we pass it to the mod trainer.fit method. So we pass the train loader, which is the data loading mechanism, and we pass the Sinclair model that we defined earlier. And when we run this fit, it will run for maximum epochs time and produce the model. So this was defined here. We can run it here, train Sinclair. We provide some base size and some different hyperparameters. These are tuned by whoever sort of provide the tutorial. That works really well. But in general, if you apply it to your data set, you would have to sort of adjust these numbers. It takes quite a while to run. Let me run this. Just to show you, like I'm just going to run it for one epoch. It takes quite a while. I would have to stop it. But to give you an idea of like, in here, we are almost like whenever you're looking at these self-supervised learning methods, you are basically saying, I have a lot of compute. I have a lot of unlabeled data. I just don't have labeled data. So that's the trade-off. Like you can't have like 20 unlabeled images and one CPU and expect that your sort of final model will be like really good. You really need like a lot of unlabeled data to have like some useful results. So it's 5% done. I would stop it here, and I would load a model from this link, which is the same model we defined up there. And what happens is this model was trained for a day on the same, like just this method was run for like 1 day for 300 epochs on a GPU, and then it's available on the internet, so we can download it here. And now, so now we have the model, the Sinclair model that's trained. So we have this thing. We have this thing which can provide us the ZI. So we have this model available to us. Now, how do we use it? So we can use our training and test data set and this model to generate features for us. So I wouldn't go through this block of code, but what it basically does is, given the Sinclair model and given the training image data, give me, like, in this training image data, we have images and labels. Now, in this output, we would have features and labels. So what features? The Sinclair features, the ZIs and the. So if I run this, okay, so in this data set, we have 5,000 examples, and each example has a feature size of 512. And if we look at the labels of this, the labels are just 5,000 labels. So that's the training data set, and if I replace it with the test data set, so we just only have 8,000 total test examples. So this is so the training and the test image data sets are pretty small. Like 5,000 images are not enough to train a good model from scratch. But if we use this Sinclair features, then let's see how do we do what the performance is like. So here we will train a logistic regression model using the Sinclair features. So let me just quickly recap and show you like what we did so far. So we had like so far we had a data set. So we had a data set which consisted of 100K unlabeled data and 500 images per class for training. So basically, so we have 10 classes, so we had like 5,000 total images for training. So if we train a model just based on this training data, which is like just the total is like 5K, then we are supposed to see really bad results. So what we did was we used self-supervised learning or the Sinclair model on the 100K unlabeled images, right? And now we have a Sinclair model. So this resulted in a Sinclair model. Then we use this model to generate features for us. So we feed in these 5K images into this, and it gives us another 5K feature. So here are the images, which are 96 by 96 by 3 or 3 by 96 by 96. And here we would have 5K, just 512 dimensional. I think 512 was the dimension there. Yeah, 512. So it will give us 5K 512 dimensional features. Now, it's equivalent to before we had the example of 2 circles. So it's like here we have those 2 circles, and this is now a good representation, hopefully. Now we have like those points, the squared points where we can just like if this was here like this, then these are like the 2 classes here. So I'm hoping that these features are like this. So what I'm trying to do, I computed these 512 5K features. I'm going to apply a logistic regression on this features data. So let's look at the logistic regression. So the particulars of the logistic regression models are not really interesting. It's very similar to how you would train any other network. So we have the model is nn.linear PyTorch linear layer. Its inputs is 512, going to be 512, and the number of classes is 10. So inputs and outputs. And in the training step, we calculate the loss, and the loss is really a simple cross entropy loss. So we have the batch of features and labels. We pass it through our model. We calculate the loss function, and we return the loss function. So that's the logistic regression model. So I'm going to run this here. And then similar to what we did for the feature learning part, we need a trainer for the logistic regression. So I'm just going to run the trainer as well. And now ignore the rest of the parts. But let's say if we have 500 images, I'm going to just train the logistic regression on 500 images per class. And so it's going to train the logistic regression model rate. So up there. So it's training on 500 images per class. So here we are using 500. But a question is, like, can we use just like the 500K, 5K means 500 per class? Can we use like, what if like I'm working with a medical imaging data set, and 500 images are like a lot to label. So hey, the radiologist or like the expert said, I can only do 10 images per class. Or what if like you found other people and they could only do 50 per class? Wouldn't it be nice to know like what the performance would look like if I only had 50 images or 10 images per class? So we are going to see that as well. So that I can set that up here 1050, and I can rerun the training. And it will take a bit of time, like a minute or so. But once it's done, we can print the results. And we see here that the test accuracy, if we only have like 100 images in total, 10 images per label, we would get a 62% accuracy. If you only had these 10 images and no simpler and only logistic regression, 60% would be impossible. But since we have the simpler features and we have like a really good representation, even with 10 images, we are able to get the 62% accuracy. If we increase the number of images to 50 or 500, the accuracy drastically improves. So this is basically the advantage of self-supervised learning, that it used a lot of unlabeled data. So if you don't have many labeled images, you can still get a decent accuracy. Just for the sort of comparison, if you want to randomly assign things to different classes, then the accuracy would be 10%. So it's like 50%, 50 points better than random. Similarly, 74 is a decent accuracy. So that's pretty much it. The training of the logistic regression finished. So this is from a previous run. Let's see what it did this time. Yeah, so very much similar numbers. So that brings me to the conclusion of this this workshop. One final sort of thing, we didn't go over a medical imaging data set, but these techniques are being actively applied to medical imaging. The data set sizes are pretty large, so it's usually beyond the training capability of Colab. But I would highly encourage you to look at 2 articles before jumping into these things, and I'll open these here. So one is a blog post and a related paper from Google on medical image classification, and I'll just briefly highlight like what they did was they basically take 2 pictures or 3 pictures of the same pathology. So like if you're getting a chest X-ray, usually people have multiple chest X-rays, and then they could sort of predict whether this chest X-ray is from the same patient or is it from a different patient. And so they don't use these augmentations that we saw on here. So they don't specifically use like this sort of augmentation, but what they do is like having one image from the same patient, another image from the same patient, a third image, and so every other image is a negative example, and the images from the same patient are positive examples. So that's so looking at the results, there's a 1% increase in accuracy on the chest X-ray data set, and about 7% increase in accuracy for some skin lesion detection data set. So this is just some sort of like good to know sort of things, and then a comparison of the different self-supervised methods in medical images is provided in this article. So and provides the code as well. So earlier there was a question like what to use. So articles like these could really guide you into like, okay, I'm deciding between Sinclair and masked autoencoders, like what are the trade-offs? So those kind of papers could really help you answer those questions. Okay, so that's the end. I'm open to take any questions.
Yeah, perfect. Thank you so much. That was very comprehensive. If you have any questions, please feel free to put them in the chat. Okay, thank you very much. A very interesting talk. Going a bit beyond classification, do you know if there's any applications of SSL to image segmentation? Would this make sense to do, at least to suggest candidate segmentation classes? Yeah.
Yes, definitely. So this is not image classification is basically a very simple task. So people basically default to it when describing some technique, but it's generic. So the representation is generic. So you could definitely apply it to image segmentation or other sort of other tasks that are done using supervised learning. So basically, you can learn a good representation for any sort of supervised learning task.
Thank you for your question, Benjamin. Thank you, Najeeb, for answering. Please share the notebooks and articles later. Oh yeah, the notebook has been shared actually, but I'll just do it again. If you go on Gumroad, they're there as well. One second. And if there's any other question, please go ahead and ask as well. Here's the notebook again. Let's see if there's any other questions. Yeah, I don't see another question right now. We also had a bit of discussion before we went into the code as well. So I think this will conclude to this session. Thank you so much, Najeeb. That was really, really interesting and engaging, and with all the chalkboard talk as well. I really enjoyed how you described the formulas, the loss function corresponding to the code. I think that really helps everyone understand too. So thanks so much for your time today, Najeeb, and for everyone else. We'll come back next Saturday, but before that, we'll have a tutorial session on Thursday at noon with 2 of our mentors. Yeah, an email will follow. Great. Thank you so much. Have a good weekend.
Thank you so much. Thanks everyone for attending. Yeah.
Great. Thank you, Najeeb. Bye-bye.